In our fourth and final video for Chapter 7, we're going to be looking at carbocation stability to start with. And the reason we're looking at carbocation stability is that we saw carbocations show up in the SN1 mechanism. And it turns out that we can use carbocation stability to explain the rate trends that we saw for the SN1 mechanism. So we can classify carbocations as primary, secondary, or tertiary, although we can even throw in an extra one, the methyl carbocation. So here are the carbocations. And like I said, we can classify them as primary, secondary, tertiary, although there is technically the methyl carbocation. We'll find that as we increase the number of alkyl groups, the R groups, we will increase the stability of the carbocations. So tertiary, more stable than secondary, more stable than primary, which is more stable than methyl. So carbocations get more stable as we add more alkyl groups to them. Now for this, we're going to look at number 63 on the in-class assignment. This is an easy problem. We're just going to rank some carbocations in order of increasing stability. All right, so we'll look at this one. So here, if we can just figure out what kind it is, then we're halfway there. So if we look at this one, we've got a tertiary carbocation, there is a secondary carbocation, and this one is a primary carbocation. So the least stable is going to be this one, because it's primary, and we can put that there, that's primary. This one's secondary, and this one is tertiary, so this is the most stable. So the least stable is primary, and the most stable is the tertiary. All right, on this one, we can look and see what kind of carbocation. This one is a primary carbocation. This one here is tertiary, and that one is secondary. So this primary one is the least stable, all right, and this tertiary is the most stable. Now, hopefully you guys understand that the secondary one is in between the least and the most, but just to be absolutely clear, yes, that is the case. Okay, so how can we use this to explain our rate trends for SN1? Well, first, let's look at why we have the carbocation stability. There are two effects that we're going to look at. One is called an inductive effect. And inductive effects are the pull of electron density through sigma bonds by electronegativity differences. And it turns out, if we look here, alkyl groups, they donate their electron density. I'm going to show you here that carbon that is in the middle is sp2 hybridized, whereas the alkyl groups are sp3 hybridized. Well, it turns out that the more S character that a carbon has, the more electronegative that it is, the more that it pulls electron density towards it. So we'll find that that alkyl groups will donate electron density because they're sp3 hybridized to the sp2 hybridized carbons, just because the carbons are a little bit more electronegative. Now, another aspect of this is just looking at the polarizability of an alkyl group versus a hydrogen. Hydrogen is just one atom with one electron, whereas an alkyl group is 4 atoms with a whole bunch of electrons. So at least the methyl is 4 atoms. So it donates all kinds of, it has all kinds of electron density to potentially donate to that carbocation, to the positive charge. You'll see if we look at the electron density maps here, the electrostatic potential maps for a methyl, primary, secondary, and tertiary carbocation, that as we add more alkyl groups, it helps to stabilize that positive charge and make it so that the positive charge is essentially more spread out. It disperses that positive charge. And to the extent that you disperse the positive charge, you stabilize it. So the other effect that we want to look at is something that's called hyperconjugation. And so we can also use hyperconjugation as a way of thinking about carbocation stability. All right. So here I've got a methyl carbocation, and over here we've got this is the ethyl carbocation. It's a primary, or no, I'm sorry, this is the propyl carbocation. It's a secondary carbocation. And when you have an alkyl group, those alkyl groups are sp3 hybridized, and it is possible for some of the electron density in this orbital to be donated to the empty p orbital that is on the carbocation carbon. And that's simply because they have similar symmetry, right? You can see the two different lobes of the electron density here are the electron wave, the wave function. They can donate their electron density into that empty p orbital with the positive charge. All right. With the methyl carbocation, the hydrogens don't have those orbitals and thus the electrons to donate their electron density in there. And so that helps to explain carbocation stability to some extent. Now, I am going to tell you that hyperconjugation is kind of an arm-waving explanation of carbocation stability. And arm waving, just so everybody understands what arm waving is, when you do arm waving, let's say you're trying to explain something, but you don't want to explain the math, you wave your arms a lot in hopes that people will understand it. Yeah, so arm waving is when we don't want to show the math. There is something to hyperconjugation, but it is kind of, like I said, an arm waving explanation. I don't want you to think that that you have to memorize this. The most important thing about carbocation stability is alkyl groups donate electron density. Whether they do it just because they have more electrons or they do it by hyperconjugation doesn't really matter. The more alkyl groups you have, the more stable the carbocation is going to be. So now we want to look at something that we call the Hammond Postulate. And we're going to come back to the Hammond Postulate over and over again throughout the rest of this semester and going into the second semester of organic chemistry. The Hammond Postulate is one of the most important concepts in organic chemistry. I don't know if it's one of the most important, but it's a very important concept in organic chemistry. We use this all the time. The Hammond Postulate states, quite simply, that the transition state of a reaction resembles the structure of the species to which it is closer in energy. And that species can either be the reactant or the product. Now, let me show you by a picture, because reading that definition, you may have to read it several times to get what I just said. But I'm going to show you a picture. If you have an endothermic reaction, the transition state is going to, well, for any reaction, the transition state is somewhere in between your reactant and your product. But for an endothermic reaction, the transition state more closely resembles the product because it's closer in energy. For an exothermic reaction, the transition state more closely resembles the reactants because it's closer in energy to that. So that's what the Hammond Postulate tells us, is that the transition state is going to resemble the thing that it's closer in energy to. That's sort of the quick way of thinking about it. So whatever it's closer to, that's what it looks like. All right. Well, let's go back and look at our trends. For SN1 reactions, we know that tertiary alkyl halides react faster than secondary. Secondary goes so much faster than primary and methyl that primary and methyl don't really happen for SN1. So we'll find that that the carbocation stability is that tertiary carbocations are more stable than secondary, which are more stable than primary, which are way more stable than the methyl. And so the rate increases as the number of R groups increases, the number of alkyl groups. The stability of the carbocation increases as the number of R groups on the carbocation increases. All right, and the Hammond Postulate will predict this relationship. Now, the product doesn't necessarily tell you how fast the reaction goes. It's the transition state, it's that activation energy that will predict how fast the reaction goes. So there must be something, and the Hammond Postulate tells us this, about the stability of these carbocations and how that affects the transition state. So here is a generic picture, a generic reaction coordinate diagram for, we've got a reactant. It's an endothermic step. And so here are our products over here. And if we go, let's say we're doing the red reaction, well, the transition state is going to have a certain energy. Well, if you can lower the energy of this intermediate, then you can then that means you will also lower the energy of the transition state, because anything that will stabilize this product is going to stabilize the transition state. The transition state more closely resembles the products. So again, anything that stabilizes the products is going to stabilize the transition state. So in an endothermic step, the transition state resembles the products more than the reactants. So the transition state looks like the products. Anything that stabilizes the products lowers the transition state and thus lowers our activation energy. Anything that lowers the activation energy is going to make the reaction go faster. So when we compare these two, the blue line here is going to go faster. That's going to be a faster reaction because it has a lower activation energy. And the reason it has a lower activation energy is that transition state's lower in energy. And the reason that transition state is lower in energy is because this product is lower in energy. All right, now for exothermic reactions. Well, in an exothermic reaction, we will find that the transition state more closely resembles the reactant of that step rather than the product. Well, anything you do to lower the energy of the products isn't going to do much to the transition state energy, because again, that transition state is going to more closely resemble your products. So, I'm sorry, your reactants. So anything that stabilizes the reactants would help to stabilize our transition state, but that's not really what we're going for here. So here our products, if we decrease the energy of those products, it does little to that transition state, little to the activation energy, and therefore the reaction rates are largely unaffected. So if you want to lower the energy of the products to speed up a reaction, it helps if your rate determining step is endothermic. And that's exactly what happens with an SN1 reaction. So let's look at the Hammond postulate in application to the nucleophilic substitution unimolecular. All right, so since the secondary carbocation is less stable than the tertiary carbocation, the activation energy for the secondary pathway is larger than the activation energy for the tertiary pathway. All right, so here we have to form a secondary carbocation, and on this one we're going to form a tertiary carbocation. If we look at the reaction coordinate diagram, we will see that for our tertiary, we have a lower energy of our intermediate, which is the product of that step. That makes that have a lower transition state energy and thus a lower activation energy. The secondary is higher in energy, therefore it has a higher transition state energy and also a larger activation energy. So now we want to use what we have learned about our mechanisms to determine which one is going to happen. But to do that, we need to look at 4 different factors. And most of this is a review of what we've talked about in this chapter. But we want to talk about these 4 different factors. The first factor that we want to look at is the nature of the alkyl halide. All right. This will do most of our prediction work for us to determine, is this going to be SN1 or SN2? The nucleophile, we'll find that whether we have a strong or a weak nucleophile will help us to predict whether we're going to have SN1 or SN2. The quality of the leaving group, is it a good leaving group or a poor leaving group? Now, I'll warn you that the leaving group doesn't really predict whether it's going to be SN1 or SN2. What the leaving group will do is it'll predict whether the reaction will go faster either way. It doesn't help us choose whether it's SN1 or SN2. And then the solvent. We know that, and I've mentioned this before, that polar protic solvents tend to favor SN1 and polar aprotic solvents tend to favor SN2. So let's go through these in more detail. The identity of the alkyl halide. Turns out this is probably the most important factor in determining whether your reaction is going to be an SN1 or an SN2 mechanism. For SN2, methyl and primary are going to favor SN2 exclusively. They just, because you can't form methyl and primary carbocations very easily, SN1 is just not a viable option for these. Conversely, the tertiary alkyl halides are going to only undergo SN1. Because this alkyl halide is sterically hindered, we can't do that backside attack for the SN1 mechanism. The only real overlap here is with the secondary alkyl halides. Secondary alkyl halides, it's possible to do both the SN1 and the SN2. So when you have a secondary alkyl halide, you really need to look at the other factors to help you determine whether your reaction is going to go SN1 or SN2. So many reactions you can determine the mechanism just by looking at this. Once you know this, then you can predict that mechanism. However, if it's secondary, we need to look at the other factors. All right, so now let's look at strong nucleophile versus weak nucleophile. Strong nucleophiles, and these are ones that typically have a negative charge on the nucleophile, and when they are present in high concentrations, those strong nucleophiles tend to favor SN2 reactions. All right, so hydroxide, that's a strong nucleophile. We've got that negative charge directly on that atom, so that is going to favor the SN2 mechanism. Weak nucleophiles, and many of your weak nucleophiles are going to be either very weak bases or even neutral nucleophiles like water and alcohol. They're going to favor the SN1 by decreasing the rate of the SN2 reaction. So the strong nucleophiles favor the SN2, weak nucleophiles don't favor the SN2, so they tend to favor the SN1. So here, if we have the same alkyl halide, the secondary alkyl halide, we're first going to do the first step where we lose that carbocation, or we lose the bromide to make a carbocation, and then our weak nucleophile is going to come in and react with this. Now, since there are two possible sides, we can react on the front, from above, or from below. You can think of it as front and back or above and below, depending on how you're looking at this. If it comes from above, you're going to get this isomer, the cis isomer, and if it comes from behind or below, you're going to get this particular isomer. All right. Now, one thing I want to point out about this is that A has no stereogenic centers. So this, we're not doing racemization here. We are converting this from this isomer to a cis and trans isomer. So these are diastereomers of each other. So this is not racemization. This is just changing from one particular diastereomer to both. And because these are not equal in energy, we wouldn't necessarily get a 50-50 mixture of these. So I just point that out because sometimes people will confuse that. These are cis-trans isomers, and all cis-trans isomers are diastereomers, just as a reminder. Okay, so now that we've done that, let's look at leaving group effects. This is not one that you're going to use to determine whether it's SN1 or SN2. This is just something that will help you to determine whether the reaction will go faster or slower. So better leaving groups increase the rate of both SN1 and SN2 mechanisms. Changing the leaving group doesn't really favor one mechanism over the other. So fluoride is a pretty bad leaving group. Chloride's good, bromide's better, iodide is the best as far as leaving group goes. But by changing from one to another is not really going to change which mechanism you're going to follow, because both the SN1 and the SN2 require that the carbon-halogen bond be broken in the rate determining step. All right, solvent effects. Polar protic solvents will favor SN1 reactions, and that's simply because the polar protic solvents we'll find that the ionic intermediates are stabilized by solvation. Particularly the anion is more stabilized by solvation. So polar protic solvents tend to favor the SN1 reaction. Polar aprotic solvents tend to favor the SN2. And the reason is because it's aprotic, it doesn't have a very strong interaction with your anion, and your anion is typically the nucleophile. So your nucleophiles are not well solvated and they become more nucleophilic. Because they become more nucleophilic, they are more likely to do SN2 reactions. So just memorize polar protic SN1, polar aprotic tends to favor SN2. All right, and then here is the rundown of all the possible things, and I'm just going to review them real quick before we do number 70 on the in-class assignment. So first thing is the alkyl halide, primary and methyl is probably going to go by SN2, almost certainly by SN2. Tertiary alkyl halides by SN1, and secondary, it depends. All right, for the nucleophile, strong nucleophiles tend to favor SN2 over the SN1 mechanism. All right, and weak nucleophiles will tend to favor the SN1 over the SN2. All right, we'll find that our strong nucleophiles usually have a negative charge, and our weak nucleophiles are usually neutral. Then finally, our solvent effects. Polar protic solvents, as you'll see, polar protic solvents tend to favor SN1, and polar aprotic solvents tend to favor SN2. Okay, so let's look at number 70 on the in-class assignment. So here we want to predict which mechanism is going to occur and then draw the products. So we want to predict which mechanism is going to occur and draw the products. All right, so let's identify all the factors. So we have a primary alkyl halide. Since it's primary, that's almost certainly going to be SN2. If we look at this, we've got a strong nucleophile that also favors SN2. So I'm going to put strong nucleophile. And if you look, acetone is polar aprotic. And so I'm going to put aprotic. So all of those things favor SN2. So I'm going to put SN2 here. All right, now it says also draw the products, include any stereochemistry. This is kind of a trick. If you look, there are two methyls attached to that second carbon there. That means that this is not a stereogenic center. That is just cleverly drawn to make you think that it's a stereogenic center, but it is not a stereogenic center. So we will do 1, 2, 3, 4, 5. And we're going to replace the bromide with the cyanide ion. So we'll have CN. And then I'll go ahead and put the bromide, because that is also produced. And here, I'll go ahead and put that, even though there's not a stereogenic center there. So SN2, that's not a stereogenic center, so we don't need to worry about it. It was just kind of drawn weird. All right, on this one, so we'll look here. This is secondary. Secondary means it's up in the air. It could be either. Here we have a strong nucleophile. All right, strong nucleophile tends to favor SN2. And then DMSO is polar aprotic. And if you're trying to remember which ones are protic and which ones are aprotic, go back. There's a list earlier in the chapter. So polar aprotic tends to favor SN2. So strong nucleophile, polar aprotic with secondary, we're going to say it's probably SN2 mechanism. So now let's look at this. We'll see that this is a secondary, the secondary alkyl bromide. There are 4 different things, so that is a stereogenic center. And with SN2, we get inversion. So 1, 2, 3, 4, 5, 6. So I'm going to draw that chain. I'll go ahead and draw that methyl that's there. And so since that methoxide group is going to come in from the back side, so we'll have hydrogen that comes forward and OCH3 that is back there. And we'll put bromide. And then I'm going to put a note here that this has inversion. We get inversion at that stereogenic center. Okay. On this one, let's look at the things here. This one is tertiary. Well, that tells us it's probably SN1. The methanol is a weak nucleophile, so that also favors SN1. And methanol is a protic solvent, and so that also favors SN1. So this is going to be SN1. I meant to make that a subscript. Sorry about that. All right, if we look at this, this is not a stereogenic center, because if we look at the ring, these two are identical, those two are identical, and then that is the same carbon. So that is not a stereogenic center. There's no cis-trans chemistry or anything going on here. So we don't need to worry about stereoisomers. So we're just going to have one particular product. And we'll have OCH3. And I'm not even going to draw the wedges in the dash because it's not necessary. CH2, CH2, CH3. All right. And then as far as the other thing, I'm going to put HBr as our product, because the bromide comes in after we add this. We're going to have an O, so HOCH3 plus. We'll have a positive charge on that oxygen, and we'll have to deprotonate it. We're going to deprotonate it with a bromide ion, which, okay, bromide doesn't really do well at deprotonating, but we're going to just say that it does. So we'll put that as our product. All right, next. So here we've got carbon, 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 and then iodide. So this is a secondary. So that could go either way. We've got, let's see, so secondary. This is a weak nucleophile. All right, that's acetic acid. That's not a strong nucleophile. It's neutral. So we'll say weak nucleophile. And presumably we're going to use that as the solvent. So that is a protic solvent. So now that we've done that, since that so protic, it's weak, this is probably going to go by an SN1 mechanism with a weak nucleophile and a polar protic solvent. That means that we will get racemization. So I'm going to draw these. So carbon, CH2, CH3, hydrogen there. And so we'll get one that has retention. So we'll have CH3 and then O, carbonyl, CH3. That's the acetate group. All right, so we'll get that as one of our enantiomers. And then the other one, we'll just have it come out like this, O, C, CH3, and then CH3 there. All right, and then our leaving group is going to be iodide, and we'll go ahead and we'll put that as HI. Although that's a little iffy that we did actual HI, but we would have something that's there to deprotonate in that final step. But there we go. So we would get a 50-50 mixture. And just as a reminder, this is called racemization. All right, so racemization. This would be a racemic mixture, and this is racemization. All right, let's look at this. Here we've got a secondary alkyl halide, so I'll put secondary. We've got a strong nucleophile, and DMF is polar aprotic. Well, all of those things tend to favor SN2 mechanism. SN2 mechanism. All right, with that SN2 mechanism, that means we will get inversion of this. It's not going to affect this one because that stereogenic center isn't where the it isn't where the nucleophile comes in. So we would not get any change there, but we would get inversion at this one. So we will get one product. And we'll go ahead and draw that. So that will remain the same, that ethyl group. But then here we're going to get OCH2CH3. And then bromide will be our leaving group. And this, we're going to have inversion. All right, we'll have inversion at that stereogenic center. All right, let's look at this final one here. This one is also secondary. It is a weak nucleophile. And assuming that that's the solvent, that would be a polar protic solvent. Okay, so that is going to favor the SN1 mechanism. And with SN1 mechanism, we don't protect the stereochemistry. Now, as we saw on the example on the overhead a little bit earlier, on the presentation a little bit earlier, this does not have any stereogenic centers, but it does have cis-trans isomerism. So this is the cis isomer of this compound. The trans isomer would be where the chloride is going the other direction. But we would get conversion of this to both cis and trans. So we will get two possible isomers here. So one, so there is our methyl. And then we get OCH2CH3. That would be one of our isomers, and that's the cis isomer. And we would also get some of the trans isomers, so OCH2CH3. All right, and plus the chloride, and it's going to deprotonate, so I'm going to put HCl, and we're going to just use the chloride to deprotonate in that final step. All right, so there we go. Again, this is not racemization. We would not necessarily get a 50-50 mixture here because these are not equal in energy. This one would be lower in energy than this one, so we probably get a little bit more of this one, but thanks to the Hammond postulate and that being an exothermic step, we're probably not going to have a huge difference between those two. All right, so let's go back to our presentation here. All right. Earlier in the chapter, I mentioned how we don't get reactions between we don't get nucleophilic substitution reactions on vinyl halides and aryl halides, at least not the SN1 and SN2 varieties. And we're going to look at the vinyl halides, but the same logic applies to the aryl halides. When we do this, is for the vinyl halides, if we were going to attempt an SN2 mechanism, the nucleophile would be forced to come in at the same plane as all the other atoms that are in that double bond. And so our nucleophile would be forced to come in here, and that's going to be fairly crowded. Even if these are just hydrogens, that's going to be somewhat crowded. So it's unlikely that we would be able to do this. On top of that, breaking the carbon-halogen bond is going to be more difficult because the carbon-halogen bond is stronger in when you have an sp2 hybridized carbon. So the carbon-halogen bond is stronger there. All right, so SN2, just not very viable. SN1, the reason it is not viable is that if we lose that halogen to form a carbocation, the carbocation that we're going to get is a vinyl carbocation, which is sp hybridized. And it turns out that that is very unstable. So sp hybridized carbocations are very unstable and it's just not likely to happen. All right. Using similar logic, we can see that the Aryl halides are not going to do the SN1 and SN2 reactions as well. So this is just a little section to remind you, if you have an sp2 hybridized carbon bonded to a halogen, this chapter doesn't apply to it because we can't do those reactions. All right, we want to look at something that we call organic synthesis. And this is something that I want you to develop your thinking about as we move on through the end of this semester and getting into next semester. And that is how to do organic synthesis and how to think about doing organic synthesis. It's really just, it's a systematic way of coming up with something. If you have one kind of compound, how do you come up with another kind of compound? Since in this chapter we were focusing on alkyl halides, then I was showing you all kinds of ways that you can convert alkyl halides into different functional groups. So you'll notice here we have now come up with a way to make alcohols, a way to make ethers, a way to make esters, a way to make carbon-carbon bonds. Turns out making carbon-carbon bonds is a hugely important thing in organic chemistry. How to make carbon-nitrogen bonds, and how to make carbon-sulfur bonds. So we can make all of these functional groups using alkyl halides and either SN1 or SN2 reactions. So as you go through organic chemistry, I want you to remember how to come up, how to make these things. So I don't want you to forget these reactions. So you will want to know how to do these kinds of reactions. We are going to find that SN2 reactions tend to be more useful and more reliable than the SN1. And we'll talk about that a little bit more in the next chapter when we discuss the elimination reactions. When we form that carbocation, all kinds of interesting things can occur, and sometimes those interesting things give us products we don't want, and so SN2 turns out to be a more viable option for organic synthesis. And with this, we can make all kinds of pharmaceutical compounds, pesticides, polymers, and many other things. There's a whole industry, a chemical industry, based on making compounds using synthesis, and like billions and billions of dollars are on the line, and many lives can be saved, particularly with the pharmaceuticals, can be saved by doing clever organic synthesis. So in order to do this, we want to think backwards when we're doing the organic synthesis. We want to be able to look at a product and say, well, how could we have come up with that using SN1 or SN2, and mostly SN2 in this particular chapter. So we want to think backwards. What starting material and reagents would we need to make that product? So if we're doing a nucleophilic substitution, then what alkyl halide would we have needed, and what nucleophile would we have needed to make that particular product? So here's an example. This is an alcohol, the 2-methyl propane 1-ol. I would call that isobutanol. So we wanted to make this isobutanol. How would we go about doing this? Well, clearly this chapter was all about making new bonds between carbon and something. It would be the carbon and the oxygen here. So that means that this would have been our nucleophile. So hydroxide would have been our nucleophile, and that this would have been our alkyl group, and there would have been a halogen there, like bromine or chlorine. So here we picked bromine, but we could have picked chlorine as well. So we can do that nucleophilic substitution, second order, right, SN2, and we could have gotten this. So we're going to look at numbers 79 and 82. These are the last two problems in chapter 7. Thank goodness. All right. All right, so fill in the appropriate reagent or starting material in each of the following reactions. Well, I didn't leave enough space here to put in what that starting material or what that reagent would be. But you'll see that we've got 1, 2, 3, 4, 5, 1, 2, 3, 4 carbons, and then on that second carbon we've got a methyl, so 1, 2, 3, 4. So this carbon chain is part of the backbone. There's our alkyl halide. So really, we kind of want to think about this is that we can kind of break that molecule here, and this would have been our nucleophile, and this part would have been our alkyl halide. So our nucleophile, and I'm just going to write it over here, would have been cyclohexoxide. So we would have the cyclohexane with an oxide group on it, and that would have been our nucleophile, and that's it. So you can kind of look for where is the bond that we formed, and I just drew a little dotted line here to indicate that that's the bond that we formed when we were doing this, and that's how we would get it. All right, so here we've got chlorocyclohexane, and we want to convert it into this alkyne. Well, clearly the new bond that we formed was this one, and so we need this as a nucleophile, and that as a nucleophile is going to be this, and this is the acetylide. That is the acetylide anion, and it's a great nucleophile. Now, in reality, of course, we can't just have these by ourselves. This would be like sodium cyclohexoxide, and this would be sodium acetylide, but that's how that would work. All right, here we have the azide, and so azide, we made a new bond between azide and it looks like a cyclohexane ring, and so it looks like we could have picked this, and I'm just going to write that. So chlorocyclohexane would have worked. Now we could have picked bromocyclohexane if we're feeling kind of decadent and rich, but chlorocyclohexane would have been the more affordable option. Doesn't work as cleanly as the bromo, but it is definitely more affordable. All right, so all of those were SN2. This one is also SN2, but you'll notice that we've got some interesting stereochemistry here. So in order to get this, clearly this is the new bond that we had formed, is between the sulfur and the cyclohexane, but you'll notice here that we've got a particular stereochemistry. Since we get inversion at the carbon where we're doing the SN2, that means that our halogen would have needed to be the other direction. It would have needed to be the other isomer. So, all right, so we could have picked, I'm going to pick the bromo here, but we could have picked chloro as well. All right, so this would give, this plus this would give us that. So here we have trans. When we do the chemistry, we would end up with the cis. If we had picked the cis to begin with, we would have ended up with trans for the product. So that's why we didn't pick the cis isomer here. All right, we've got one more problem, and this one is kind of fun. And again, I think of fun in different ways than other people think of fun. So suppose you have 4 compounds, so methyl iodide, and then we've got this cyclohexane, 1-iodo, 1-methyl cyclohexane, and then here we've got sodium methoxide, and then we're just going to call it whatever this alkoxide is. It's an alkoxide, and we want to make this. So there are 2 possibilities in terms of making this. I'm going to draw this a little bit bigger here. All right, so there's that. Oxygen, CH3. So there's 2 ways to think about this. We could have formed this bond or this bond. If we form this bond, then that means that we would have used this alkyl halide and that alkoxide. And if we formed this one, that means we would have used this alkoxide and that alkyl halide. So let's draw those out. We're going to have 2 reactions that give the same product. and then we want to pick which one is likely to work better. So let's start with this one. All right, so if we try to do this, so our methoxide is our nucleophile, and then here is our alkyl halide. On the other option, we had CH3I plus and here I'm going to put negative and then Na plus, just to emphasize that that's the alkoxide. We would have this plus the methyl iodide. All right, well, this is a strong nucleophile, which means that we're probably looking at trying to do an SN2 mechanism. And when we look at this, this is a tertiary alkyl halide, and this is a methyl alkyl halide. I could have put just CH3, but that's the methyl alkyl halide. Well, we know that SN2 works a lot better on primary and methyl, and it doesn't really work very well on tertiary alkyl halides. So this is going to be not favorable because we have a tertiary alkyl halide, and doing SN2 with a tertiary alkyl halide is just, again, not a very favorable reaction. And so this one would be our favorable or preferred. Yeah, so I'll put favorable, but that would be our favorable pathway rather than doing this. Okay, this one, the only thing that's really a problem with this is that here our nucleophile is somewhat sterically hindered, but because we have the methyl iodide, this probably would be a viable pathway. All right, well, that is the end of Chapter 7. Chapter 8, we're going to do a similar types of reactions. We're going to be looking at elimination reactions instead of substitution reactions, but we will be using alkyl halides. So look forward to that.